10:35, we are ready for our morning technical session. My name is Joshua Li from OSU. So Dr. Norb Dilot, he cannot join us today, and I'm going to moderate this section. So this morning we have 4 presentations. Each presentation only got 20 minutes, including questions. So if you got any questions, so raise your hand. We have 2 students going to pass the microphone to you. So the first presentation is co-presented by Dr. Darwin and Mr. Walt Peters. So Dr. Darwin, he's the chair and Dan Acker Distinguished Professor of Civil, Environmental, and Architecture Engineering at the University of Kansas. He holds the PhD from Urbana-Champaign. He has conducted extensive research in structural engineering and concrete materials. He's a fellow of multiple prestigious organizations like American Association for the Advancement of Science, the American Concrete Institute, and Structural Engineering Institute of ACE. Mr. Walt Peters has worked for ODOT in the bridge division for the last 50 years. He right now is serving as the assistant bridge engineer for maintenance. He primarily coordinates bridge research, bridge inspection contracts, and specification. Walt has and his wife has 3 kids and 6 grandkids. Welcome, Dr. Darwin and Mr. Peters.
Good morning. Hope everybody got some nice relaxation during the break. So this is about bond behavior of epoxy-coated reinforcing bars in non-proprietary UHPC. So the non-proprietary is usually a little less expensive. The outline, we're going to talk a little bit about what UHPC is, the objectives of this study, research, and the findings for the research. UHPC is a very advanced construction material. It's a very fascinating material. It has very high strength, oftentimes greater than 20,000 psi, high tensile strength, oftentimes greater than 1,000 psi. Typically, we use 2% steel fibers, which is kind of the high dollar item. Contains no coarse aggregate, low water cementitious ratio, less than 0.22. This makes it pretty impervious, like we could use it in repair and the moisture can't penetrate it. So that's a fantastic property. Very workable, spread 8 to 10 inches, and I like to say it flows like molasses. Here we see a spread test. We put it in the mold, and then we pull the mold up, and it spreads, in this case, to about 8.5 inches. Some of the advantages, a couple of them, you know, when we typically splice rebar, and you're looking a lot of times at a splice with rebars 2-3 feet. When you start using this high-strength UHPC material, you can get it down to a few inches. And when we make these precast elements, like accelerated bridge construction, ABC, Adirod mentioned that, you could get these panels really close together. So that's a tremendous advantage. We have examples of closure strips here. ODOT is picking up on this technology, 281 over the South Canadian. We're building this right now. It has the full depth precast panels, and we're using UHPC to join it. And there's another one on State Highway 109 over, I forget the creek name. But anyway, also the Corps of Engineers did a bridge on State Highway 71 over Lake Eufaula. which joined some full-depth precast panels, and those were deep, like 14 inches. Existing knowledge. Most knowledge is based on a proprietary UHPC, which is high dollar, and this non-proprietary has the potential to be a lot less expensive and uses local products, so it's exciting. Existing design approaches the bond strength in UHPC based on pull-out test. This test method is not recommended for determining bond with UHPC. Objectives of this study: for the non-proprietary UHPC, perform realistic bond tests for use in design to determine the effect of size, cover, splice, spacing of the bars, and surface properties of the reinforcing steel. Develop design recommendations for splice length in non-proprietary UHPC. Okay, Dr. Darwin.
Thank you, Walt. Pleasure to be here. Good to see you all again this year. Let's talk about the research. So the work we're doing, we're using 3 different kinds of reinforcing bars. On the top, you see epoxy coated. In the middle is regular uncoated conventional reinforcement. At the bottom coated, it kind of looks like it might be the same as uncoated, but it's a little bit different. Let's take a look. Okay, so we're all familiar with looking at uncoated bar. We know what uncoated rebar looks like, epoxy coated rebar. We're also testing a textured epoxy coated rebar. This has got the regular green coating on it and then a texture coating on the top. And what we know from conventional concrete is that the texture coated bars give the same bond strength as uncoated bars, whereas epoxy coated bars gives a lower bond strength. And we want to see if we can get that same higher strength when we're doing with the UHPC. Okay, so bottom lines. I'm going to tell you what we figured out first, especially if we run out of time here. Okay, so UHPC, we can make it with ODOT approved materials. Admixtures play a big role, and you got to work with the particular materials you have available to get the best. Bond strength in UHPC is about 2 times what you get with conventional concrete, even at the same high compressive strength. Bond strength in UHPC is independent of local variations or variations in compressive strength from one batch to the next. The negative effects of epoxy coating are much less in UHPC than in conventional concrete, and the textured epoxy coated bars do give you the same bond strength as you get with uncoated bars. This is an example of the work we've done. This is all with ODOT approved materials. We batched more than 100 mixtures to try to get the right mix down. We ended up with a mix A and a mix B towards the end. 2 different sets of superplasticizers. One had a set accelerator, the other did not. Same low water cementitious material ratio. The spread a little bit higher on mix A, but a key point is the fiber distribution. That you need a good fiber distribution. Wasn't good, nearly as good on mix A as in mix B. We also looked at, here's the compressive strengths that we got at 1, 3, and 7 days. We looked very hard at the 7-day strength. You see a little bit higher strength for mix A, but mix B catches up around 7 days. And the flexural capacity was really high, especially mix B with the better distribution of fibers. Okay, so bond, and let me back up. Here, notice that we're talking at 7 days, 3,600 PSI in tension. That's pretty hefty stuff. Okay, bond tests. Okay, so first let me talk about non-contact splices. In most cases, if you're dealing with a structural engineer, most cases you deal with a contact splice. You wire the bars together. The wire doesn't do anything, but you wire the bars side by side, and you have enough length to give an adequate capacity. But you're allowed, both in AASHTO and ACI, to have non-contact splices. The rule there is the space between the splices has to be less than 1/5 the length of the splice, and the space has to be also has to be less than 6 inches. Well, we don't have any problem with the 6 inches. We always meet that, but we're going to break all the rules on the separation, because when you have 2 precast elements, there's nothing that guarantees that that the bars are going to line right up next to each other, or be close or far away, because you're just laying the 2 precast slabs down. So you're going to have non-contact splices with space greater than 1/5 the splice length. Okay, so for pull-out tests, the early work on the proprietary proprietary UHPC was done with pull-out tests, Federal Highway. This is a picture from theirs. Notice what you have is you have a precast slab on the bottom with number 8 bars and 1-inch diameter bars cast into it, and then you cast in the test bar, typically like a number 5, at different spacings and with different splice lengths in a strip that you cast separately after the fact. Okay, this is the test we did at KU. It's a really good bond test. It's pull-out test because you don't actually push on the concrete, you push on the precast slab. So both the UHPC and the test bars are in tension, much more realistic. What do we get? Well, we tested many combinations of splice length and spacing. Let me direct your attention. Blue is the uncoated bars, orange are the epoxy-coated bars, and gray is the textured epoxy-coated bars. Notice that the textured epoxy-coated bars come up and don't look too different from the conventional bars, and that the epoxy-coated bars in most cases are weaker, but they acquit themselves quite well, especially look at the last series where they're actually stronger. Pull-out tests are not good for design, though. So the next step was an ASTM beam-end test. In this case, and I have a pointer here, but these are blocks of concrete. If you look carefully, you will see this kind of concrete looks a little bit different where the bars are sticking right into the test specimen. That's the UHPC. Splice length was 5 inches. These are number 5 or 5/8-inch diameter bars. We pull on the bar, push on the concrete away from the bar, and get different strengths. We looked at both mix A and mix B. We looked at all 3 types of bar surfaces. Notice that in all cases, the uncoated and texture-coated bars were stronger than the epoxy-coated bars, which is the orange in the middle, but that the texture-coated bars, in one case, gave higher strength than the uncoated bars, and in other cases, a little lower. But this is what we're seeing. And so between mix A and mix B had the better fiber distribution, so we stayed with that for the next series of tests. Here are splice tests. Okay, we have 2 precast sections, and if you look carefully in the middle, there's a splice region. That's our closure strip, and we have bars at both the top and the bottom. The top bars simulate reinforcing steel. At the top layer of a bridge deck, they have a 2.5-inch cover. On the bottom layer of steel, 1-inch cover. We wanted to test both of them, so we cast multiple test specimens. The test specimen, it looks like, the test procedure is on the bottom. So we have 2 supports and we have cantilever regions. We put the bar in the top in tension. We test those. And then in other specimens, we take these specimens, flip them over, and test with a 1-inch cover. So we get a variation in cover as well. We tested number 4, 5, and 8 bars. That's 1/2-inch, 5/8, and 1-inch diameter bars. That's the test specimen. You can see the precast sections at either end. This is on our lab, and in the middle is the UHPC closure strip. How do we do? Okay, so this is what we got for uncoated bars. On the vertical axis is bar force. Horizontal axis, and it's hard to see, is the product. The horizontal axis, the L is not showing so well, but the horizontal axis is the product of the splice length and the cover to the center of the bar. That's CB prime. It's cover to the center of the bar. So what you see are 3 lines. Number 8 bars are the strongest, then number 5 bars and number 4 bars. This is bar force, not bar stress. And this type of relationship where you see these kind of parallel to each other is exactly what you see with conventional concrete. Okay, how about uncoated bar? How about the coated bars, epoxy-coated bars? Similar relationship. Interestingly, the slopes on the 2 figures are identical to 3 significant figures. Here, there's not nearly as much spread between the number 8 bars and the smaller bars, but these lines are all lower with epoxy-coated bars, so they're not that strong. Comparisons to splice bars and conventional concrete. There's a large database maintained by ACI Committee 408, and they have a best fit equation. And if we take a look at for uncoated bars, the ratio of the test stresses that we got versus what you get on just conventional concrete, the ratio is more than 2 times as much. Epoxy-coated bars, interestingly, almost 2 times as much stronger in the UHPC. The textured coated epoxy, if you notice, the ratio came out to be even a little bit stronger than the uncoated bars. That tells us that texture-coated bars, are giving us at least the same strength as the uncoated bars. And by the way, all these comparisons are at the same compressive strength for both the conventional bars in ACI and the test bars we have here. Also, if you take a look at the ratio between the bar stress and the epoxy-coated bars and the stress you can mobilize at the same compressive strength in uncoated bars, ratio in our test came out to be 0.87. That compares to numbers less than 0.7 in conventional concrete, so much less impact of the epoxy coating. What does design look like? Design looks different from what you have in regular AASHTO for uncoated bars. Splice length, and in this case, the product of the area of the bar times the yield strength, minus, this is for the epoxy-coated bars, minus best fit, this is 13 times the square root of the bar diameter divided by 1.1, where CB prime is the cover to the center of the bar to the nearest concrete surface. This can be shortened if we went with the texture-coated bars. Summary, UHPC can be made from local materials here in Oklahoma. Admixtures play a big role. You got to pick the right ones. Bond strength is 2 times that what you get conventional bars, even at the same compressive strength. Bond strength in UHPC is independent of local variations in compressive strength. We saw that in our tests. The negative effects of epoxy coating are less than what you have in UHPC than conventional concrete. And textured epoxy coated bars have the same bond strength as uncoated bars. And there we go. We have like a minute or something. Okay, so if you have any questions, I'd be glad to answer them.
Dave,
Yeah.
in the splice test, how do they fare? Is it very brittle, or is it compared to conventional concrete?
Okay, the splice is very interesting. It is a pretty ductile failure because you got all those fibers in there. And the failure occurs either if the bars are closer together than the cover, you'll get a crack in the plane of the bars. If the cover is less than the spacing between the bars, then the crack goes to the surface, and you can see cracks along the surface of the bar. I mean, on the surface of the concrete parallel to the bar. And so it's, and at that point, when that happens, the bar slips, and you can see the closure strip separating from the precast sections.
The upshot from this research is textured rebar going to take the place of epoxy rebar?
The manufacturers of the textured rebar sure hope so. I mean, Sherwin-Williams is making this. They have a patent on the textured coating. There's a new ASTM A1124 out on that ASTM specification, and there are other advantages of this particular, the texture coating protects the epoxy. It's much harder to damage the epoxy. Presumably it's better in corrosion. There's tests going on right now to evaluate it. You actually have to evaluate how robust the protection is, so that you have to, the nature of actually undergo damage and without, or you try to damage it without having it penetrate the combined coating. So I think this is something that's going to be coming up pretty fast. A number of states like Illinois they're already using it for their construction. Thank you very much.